Hello, and welcome to our discussion of solving the heat equation with the Fourier transform. Specifically, we're going to work with the heat equation initial value problem, ut equals uxx for x in the reals, time t greater than or equal to 0, and the initial temperature distribution u of x0 equals f of x. So this is the same heat equation that we saw before with Fourier series, ut equals uxx, but now I'm allowing the spatial variable x to be any real number, not bounded in some closed bounded interval. So there'll be no product solutions here, no separation of variables, no periodicity. We can think of this as modeling the temperature on a really long rod. And we still have an initial condition, u of x0 equals f of x, but we have no ostensible boundary conditions. Nonetheless, when we use the Fourier transform, we usually want some sort of decay at spatial infinity to take integrals to have the Fourier transform defined. So implicitly, there's some sort of decay going on that we can suss out later. Then that's why there is no spatial boundary condition as yet apparent. So let's begin. As usual, we will assume there is a solution, and that everything involved is nice enough so that we can use all of our Fourier theorems, and we'll try to use the transform to get a formula for the solution, and then once we have a formula, we can do calculus on it and prove that it actually satisfies the differential equation. Specifically, we'll freeze time t, and we'll take the Fourier transform in the spatial variable x. I think this is the only sensible thing to do, because in the problem I'm told that time is only given for t greater than or equal to 0, whereas space x is given for all real numbers. And the Fourier transform requires us to integrate from minus infinity to infinity, and the only thing going from minus infinity to infinity here is x. So I'm going to take the Fourier transform in x. Fourier transform on u of dot t at k. What do I mean by that notation? I've frozen t, that's why t is a parameter. The x slot I've replaced with a dot to indicate that that is the independent variable of the function inside the Fourier transform, and I'm evaluating that at k. And specifically, I'll write that as u hat of kt, and that will be the integral from minus infinity to infinity of u of xt e to the minus ikx dx times the usual 1 over root 2 pi. So look at this integral. It's similar to what happened when we took Fourier coefficients for a function of two variables back in Fourier series land. I have my usual 1 over root 2 pi. I have the improper integral. I'm integrating here with respect to x. So x appears 3 times as the dummy variable of integration. T is now a parameter that's just coming along for the ride inside the integral. And then in this e to the minus ikx, k is the dummy variable, x is the dummy variable, and k is the Fourier variable. So u hat of kt, the only things in this integral that can move are the k parameter, the Fourier parameter, and the t parameter, the time parameter. X is now completely gone. I could write w, I could write theta instead of x. Inside this integral, it doesn't matter. And then if I do the transform of the x derivative, Fourier transform on uxx dot t at k, that's uxx hat of kt. So I'm taking two derivatives with respect to x. This is two derivatives in the variable with which I take the Fourier transform. So I should get out an ik squared u hat of kt, or a minus k squared u hat of kt. The important thing here is that the transform is occurring in the x slot, and the derivatives are occurring in the x slot, which is why I get the ik each time I take an x derivative. On the other hand, in the heat equation, I still have that ut derivative, and I'm not taking the transform with respect to t. So here I'll use the Leibniz rule. ut hat of kt, well, that's really defined to be equal to 1 over root 2 pi integral minus infinity to infinity ut of xt e to the minus ikx dx. And what is that? Let's pop the t derivative outside the integral, because I'm differentiating here with respect to t, but integrating with respect to x. That is t derivative on 1 over root 2 pi integral minus infinity to infinity u of xt e to the minus ikx. So that's t derivative on the Fourier transform of u. In other words, partial t on u hat at kt. So what does this do? Taking the Fourier transform of the heat equation gives me now an ordinary differential equation in t with k as a parameter. So I have partial t on u hat of kt equals ik squared on u hat of kt, which is minus k squared u hat of kt. In other words, partial t on u hat plus k squared on u hat equals 0. So now in this differential equation, what is moving and what is fixed? Derivatives are taken now with respect to time. T is the thing that moves, and k is a real number that is a parameter. For each different real k, I get a different differential equation in the t variable. Now this differential equation, once we parse through all the notation, isn't that difficult to solve. T derivative on u hat plus a constant k squared on u hat equals 0. That means that u hat of kt is a constant c of k times e to the minus k squared t. And that's just the integrating factor method or separation of variables. Now, remember your initial condition. We wanted u of x0 to be equal to f of x. So I'm taking all my Fourier transforms in u. This gives me u hat of k0 equals f hat of k. And so that tells me that the constant c of k, which is u hat of k0, has to be f hat of k. And so I can solve u hat of kt equals f hat of k times e to the minus k squared t. By the by, this is assuming that f is in L1. That was one extra thing I have to put on my problem for this to work. So now I know what u hat of kt is, and hopefully I can invert the transform and figure out what u is. Just to pause for a moment and recap, what do I need to get all of this to work? Well, I was assuming that for each t, u of dot t was in L1, and so is ux, and so is uxx, and so is f. So in order to take those transforms on the previous slide, whenever I froze t and just had a mapping depending on x, all those maps were in L1, and the temperature distribution f was in L1. And then I want to solve for u of xt, so I expect that u of xt is the inverse Fourier transform of f hat of k times e to the minus k squared t at x. And again, I'm taking the inverse Fourier transform in the k variable, so t inside these square brackets is now reduced to a parameter. So you have to have a sort of dual vision here. Sometimes the time variable t is a parameter, that's from the Fourier perspective, but then from the differential equations perspective, time t still gets to move. So make sure you know what you're transforming with respect to and what you are differentiating with respect to. Okay, so what is u of xt equals inverse Fourier transform f hat of k e to the minus k squared t at x? How can I calculate this inverse Fourier transform? Can I do anything to it? Remember that in general, the inverse transform of products is going to be the convolution of the inverse transforms under many hypotheses on everything involved. So what does this say? Inverse Fourier transform of f hat of k times e to the minus k squared t at x should be inverse Fourier transform of f hat convolved with inverse Fourier transform of e to the minus k squared t evaluated at x over root 2 pi. And this inverse Fourier transform of e to the minus k squared t, t is the parameter, k would be the variable of integration. So what's the inverse transform of the mapping k goes to e to the minus k squared t? We can actually calculate this. First, time t is greater than or equal to 0. That's given at the start of the problem. So I can always rewrite this as e to the minus k squared t equals e to the minus root tk quantity squared. Easy enough. And now I'll define phi of big X to be e to the minus big X squared. So what does this say? E to the minus k squared t is phi of root t times k. Now phi is a function that's infinitely differentiable, and it's also in L1. And we calculated in the past that phi hat of k is phi of k over 2 divided by root 2. This was a great calculation that we do in the notes, and that's very special about this e to the minus x squared function. So the inverse Fourier transform of e to the minus k squared t at x is the inverse Fourier transform of phi scaled on the inside by root t. That's what phi of root t dot means. And the inverse Fourier transform, I can also write that as a Fourier transform. So this is the Fourier transform of phi scaled on the inside by root t at minus x. You can go from the inverse transform to the regular transform by changing x to minus x. Scaling properties of the Fourier transform tell me that this is 1 over root t times phi hat of minus x over root t, assuming for the moment that t is positive, not t equals 0, because otherwise I couldn't divide. But what is phi hat? Well, phi hat is just phi of k over 2 divided by root 2. So now I have 1 over root 2t phi of minus x over 2 root t. So I popped the hat off phi and did some extra scalings. And then for my formula for phi, this is 1 over root 2t e to the minus x squared over 4t, again assuming that t is positive. Okay, that was quite a calculation. This might be a moment to hit pause and make sure you can go through all of it. And so here's what we get. U of xt is the inverse Fourier transform of f hat of k times e to the minus k squared t at x, which by convolution is the inverse Fourier transform of f hat convolved with inverse Fourier transform of e to the minus k squared t at x over root 2 pi. And we know that the inverse Fourier transform of e to the minus k squared t at x is 1 over root 2t e to the minus x squared over 4t, assuming t is positive. And we also want for this function f that the inverse Fourier transform on f hat should be f. So what do we really need about f? We need f to be in L1 and continuous and piecewise continuously differentiable, and we need f hat to be in L1. So if we assume all this about our initial temperature distribution, then nice things are going to happen. Namely, the inverse Fourier transform of f hat convolved with the inverse Fourier transform of e to the minus k squared t at x will turn out to be f convolved with the inverse Fourier transform of e to the minus k squared t at x. And because convolution is commutative, I could just write that as inverse Fourier transform of e to the minus k squared t convolved with f. And if I go into the definition of the convolution, that's the integral from minus infinity to infinity, inverse Fourier transform of e to the minus k squared t at x minus xc times f of xc, where I'm integrating with respect to xc. And then if I use my definition of this inverse Fourier transform of e to the minus k squared t, this becomes integral minus infinity to infinity, 1 over root t, e to the minus x minus xc quantity squared over 4t times f of xc. So altogether, incorporating a few extra factors of pi, u of xt is 1 over root 4 pi t, integral minus infinity to infinity, e to the minus x minus xc squared over 4t, f of xc. Okay, another good time to hit pause and make sure you can chase through all these calculations. Big picture, we used convolution, we used some Fourier theory, some inverse Fourier theory, and we used a special Fourier transform identity that we proved elsewhere, and then we just convolved with the definition and simplified things as far as we can go. Now again, we should watch out. We're demanding here that t is positive. But what happens when t equals 0? Then we know what happens. We have an initial condition for the problem. U of x0 is equal to f of x. So let's compress our notation a little. Let's put h of zeta t to be e to the minus zeta squared over 4t, whole thing divided by root 4 pi t, and we'll do this for zeta in R, not x in R, and for t positive. Then we get the following. U of xt is h of dot t convolved with f at x for all real x and t positive, and f of x for all real x and t equals 0. By h of dot t convolved with f, this is my notation of replacing the variable in which I'm convolving by a dot. So this is convolving in the zeta slot of h, as on the previous slide. And this is a formal solution. What do I mean by this? We assumed that we could solve the heat initial value problem, and that u and f were nice enough for all the Fourier theory to work. And we got this convolution solution. So if f satisfies all the properties on the previous slide, then we should be able to define a function u of xt as this piecewise function. In particular, the convolution will be defined. Then we have to check that this actually solves the partial differential equation. We've shown, you might say, uniqueness of the solution under sufficient hypotheses on u, that it decays fast enough for us to use the Fourier transform, and that the initial temperature distribution f is nice. But with this piecewise formula, is u continuous? Is it differentiable? It's always what we should ask ourselves when we have a piecewise formula, and always what we should ask ourselves if we have a formula given by a Fourier transform or a Fourier series. Do we actually have ut equals uxx? And to check all that, we would need to do some calculus and grind through differentiating the convolution, dealing with this awkward jump or piecewise condition from t equals 0 to t positive, and it would be a lot of calculus using Fourier theory along the way. We will not do that. We will be content with having this as a formal solution, but trust me that it does work out that this function u is continuous and sufficiently differentiable and solves the heat equation. Last thing, sometimes people call the function h of zeta t the heat kernel or the fundamental solution of the heat equation. Even though h itself is not really solving the heat equation, it's involved in the convolution for the heat equation, it still gets called the fundamental solution, or perhaps more appropriately the heat kernel, because kernels are things that appear in integrals when you convolve. And the very last thing I'll say is that this piecewise solution for u looks nothing like the product solutions that we got from separation of variables for the heat equation on a closed bounded interval. So we have two very different kinds of solutions for the heat equation. The product solution and this convolution solution. And it all depends on the kind of problem and application that you want to solve.